And apologies that you can't see me and only my slides. This is a one-off, will be something glitched this time, but welcome all to WeHealth. This series, for those of you who are new, is really about communicating the best possible science to the community of doers, to public health professionals, to tech professionals, to people who are fighting the pandemic using tech, to really bring out all interdisciplinary discussions and all available evidence to fight it. I am Joanna Maisel. I head up science at WeHealth, and I'm generally involved in mathematical modeling and a lot of different interdisciplinary research. Today's presenter is Aalekh Sharan. So he has had a really interesting career sort of in digital innovation and the interface between government and technology. And he's really been somebody to spearhead the whole idea of leapfrogging public health and other data infrastructures in India. I think it's, you know, not copying all of the mistakes that some of the rest of us might have made in the so-called developing nations. And I think it's really important. This pandemic in particular has really illustrated that rich countries have not necessarily done better than poorer countries. And we shouldn't just be looking to other Western countries for our solutions and really need to be learning from others. And Aalekh was involved as the lead on the data science side and on the risk algorithm side of India's contact tracing app, which is not based on the Google Apple system, which as a result we can learn enormously from because it has far more access to data than the strictly privacy preserving Google Apple protocols do. And so we can learn a lot about the disease in general as well as digital contact tracing in particular. Before we started, I just wanted to flag that, you know, you will soon be getting an invitation to the next event, which is going to be a little bit different. It's going to be a debate where we talk about the privacy effectiveness trade-off and how we should make decisions about it. And we have some really cool debaters and respondents who are going to represent a variety of perspectives. So I hope you'll all be able to join us on March 11th. But meantime, I want to hand it over to Aalekh to tell us about what they've learned from the world's largest contact tracing app.
Thank you, Joanna, and WeHealth and Oxford Big Data and Professor Luca Ferretti as well. This is a good opportunity for us to kind of discuss the key learnings from India's contact tracing initiative. And I would love to hear some feedback from this distinguished audience as well. Just let me share my screen 1 second. Can you see my screen?
Yes.
Yes, you're not in present mode, but
all right.
Just press the present and we're good. There we
Right.
go.
So to start off, the topics that I'd cover today, and just before that, a couple of disclaimers. So it's been about a year since I've been working on this. And so some of the details may not be fresh, but if you ask me a question which is detailed, I'd be happy to consult the resources we had and the documentation we have and get back to you. The second thing is I'm not, as Joanna spoke, I'm not an expert on data science or on, algorithms as some of you are. I approached this from a product viewpoint and spoke to global experts like, Professor Ferretti. I think Professor Ron Rivest is here, spoke to him as well from MIT, as well as, others who are working on it. And we try to integrate the best solution with the data that we have. So the topics I'll cover today are first, just to give you an understanding of what the situation and context were like, some of that when Aarogya Setu started, how did we evolve the risk propagation algorithm? Then why did we move into second degree tracing? We were heavily influenced by Ivan Bestringa, who's the author of the valid trace protocol. What are some other architectural decisions that we took? Some of the key results and the main learnings and takeaways that we got from this exercise. So to start off with, I think it's important to highlight that we had very clear tenets going in to the development of this app, right? So the facts were that the disease spreads exponentially, right? I mean, it's a logistic curve, and the app effectiveness in first order is similar to a reduction in activity rates in a, let's say, in an SEIQR model, which is proportional to app penetration by population squared, which means that I mean, there are lots of assumptions there, but which means that, you know, the more the app penetration there is, the more effectiveness there is squared, right? So our priority, therefore, was, you know, taking into account that we are a robust, you know, democracy, and people have, you know, privacy and security concerns as well. We wanted to optimize the number of potential lives we can save. For us, this was less of a, you know, what is the best contact tracing protocol exercise as an emergency measure. We were all in, you know, launch quickly, save lives more. And the second priority was basis A, you know, basis maximizing A, you optimize it divided by the quantum of PII used. And we'll touch upon this later. These two things seem like they're independent concepts, but they actually aren't, and they interact with each other. And, you know, those led to some of the challenges in terms of scaling this app up, you know, to 160 million users in a democracy, right? And all of what we did was on a solid bedrock of, you know, user consent and agility. So to give you a sense of the timeline, you know, roughly around 10th March, Niti Aayog, which is Government of India's, you know, national think tank chaired by the Prime Minister, along with industry experts and our, you know, Ministry of Electronics as well, they started exploring digital contact tracing. At that time, I was in India, and I had worked with Niti Aayog before as Chief of Staff to the CEO. And then I got involved around 21st March. 27th March, there were actually 3 competing solutions which were under advanced consideration for rollout by 3, you know, connected but separate teams within the government and outside the government as well. And there was a committee of experts with, you know, Professor Kamakoti from IIT Madras and others who kind of reviewed all the solutions. And by 27 March, we had got to go ahead to deploy this one. By 2nd April, you know, it had launched, the Prime Minister had endorsed it. And by 14th April, we were the fastest app in history to cross 50 million downloads, which we did in 12 days. So as you can see, the entire thing from, you know, just an idea on a paper to actually 50 million downloads was about a month. And so the environment was very much, let's make key decisions and move on in a way that can reduce the spread of the disease as much as possible. We had run some, at that point, India had like 500, you know, 400 cases per day. I had been tinkering around with these SEIQR models myself because, you know, the data was not, there was not enough data available on anything about activity rates, about transmission probabilities. Nothing was available. They were all conjectures. And so, I mean, the best we could do is run simulations and see what would happen and do some scenario modeling. And it did suggest that if we got on the contact tracing board early, we would be able to save many more lives than if the disease were close to its peak. And so we really got behind the effort and started doing that. So just to give you a quick overview of the main, you know, highlights of what it does, what Aarogya Setu does and did. The first was efficient contact tracing, which is the focus of this presentation. The early and accurate identification of, you know, people at risk so that they can be helped and they can be reached out to. The third was important, which is, you know, you need to take differential actions basis your testing capabilities and basis the risk, right? Because there's a realization that testing infrastructure, testing supply is limited. In that market, you're making this market more efficient because instead of just testing anyone, if you test people with a higher propensity of having an infection, then, you know, you're using your testing and tracing infrastructure, you know, more efficiently. The fourth was, you know, based on this solution would give us the ability to test timely. So if you test too early, as you all know, you may get false negatives with a pretty high rate. And so even for RT-PCR testing, they recommend a minimum number of days after exposure. In this case, that certainty is much higher because you have the timestamp data. And the fifth and really important one, which other countries did not take, was improved administrative understanding of where the hotspots are in advance so that temporary hospitals can be set up, so that infrastructure can be moved to those areas which have the greatest need. And so currently we have 160 million downloads. We have identified more than 2.4 million suspects. You know, India right now has around just less than 11 million total reported cases. And these are the 432,000 is the estimated number of people based on ground truth data that we have identified ahead of time before they got COVID, but they actually got COVID, right? So that is those are like the key numbers at a glance. And by the way, if there are questions, Joanna, feel free to or if you feel something is unclear, feel free to stop me, and I'm happy to explain. Now,
just say that that's actually not how it's set up. So Q&A goes in, and the questions will be at the end. But keep putting things in Q&A as we go.
Sure. So now, Aarogya Setu would not have worked in a vacuum, and I think this is really important that the government had done a remarkable job in terms of setting up digital infrastructure in the country. So I'll quickly give you the main components of that. So Aarogya Setu is over here. But we had data from ICMR, and a lot of this was architected by a joint secretary in the health ministry who ran digital health initiatives before this, but was now doing full-time COVID management pretty much, Mr. Love Agarwal. So this ICMR testing data would feed into the database in real time. So whoever got tested and were found to be positive, that information would be in a secure government server. That would help our simulation run and identify others at risk, right? And then they would get tested, and that data would again flow back in. Now, this is the simulation part. We call it a simulation because we used a Monte Carlo method to identify others at risk. Now, this data would again flow back to Ayushman Bharat, which is a national mission for healthcare for all, launched recently by the Prime Minister under PMJAY, which is a scheme in India. Now they had a huge number of call centers, so we could then contact folks who were at risk, help enforce more isolation, because contact tracing is not really effective until that message really gets out to people and they take actions basis that, right? I mean, it's one thing to know that, oh, you're at risk, but if you continue your life in just the usual manner, you might as well not do contact tracing. And then we also had a self-assessment feature on the app. I'll talk about that later, which helped identify symptoms that people may be feeling ahead of time and use that data to generate hotspot information. Now, our main objective, and this is important, was not to assign the best possible probability score in absolute terms to each individual. And so what is in this graph is a list of what we call device identifiers. The way we anonymized Aarogya Setu was, it was linked to your mobile number, but the linkage between the mobile number and the device ID was stored in a very secure server, which even I didn't have access to, and neither did any of the developers. We were only working with DIDs, so that any privacy concerns of individuals could be put to rest. So now, if you're looking at DIDs, our objective was, how do we arrange these device identifiers in a decreasing order of risk? And this comes from the first point, that the objective of this whole exercise is to make the exchange between testing and people more efficient, right? So now, even if this list is of indeterminate size, as long as the ordering of this list is intact, basis changes in the algorithm or basis changes in the environment, then we're still okay, because we want to identify the top percentiles who are at risk. That is our objective. Then the second part is communicating different risk signals to people in a simple way. I mean, communicating probabilities that you are like 21.42% at chance of having an infection, plus minus 30 is not gonna help anyone, right? So that you need to communicate it in a very simple way to people, and then communicate what actions they need to take. Now, this is an example of why we ultimately went to multiple degree tracing. This is a data from from 20th to 29th April, so very early stages of the app. At that point, we had marked around 7,000 people in the caution category, 3,200 in the quarantine, and 555 in the test category, right? Now, at that point, we estimated, basis some simulations we ran on different network topologies, that we were missing 150 people from the test category. So out of 555, that would have been around 700, 3,800 people from quarantine, which is almost double, more than double. Because we were only running first degree simulations at that time. And I'll explain what first degree is. I think every contact tracing app in the world currently uses first degree But very early on, we were influenced by Wiretrace and Ivan to move on. Our initial algorithm was also multiple degree, and I'll tell you why it was wrong, and we quickly changed it. So now, what is the basis for doing multiple degree interaction, right? So like these are an example of two different very well-known network topologies. One is called ring of cliques, right? Where you have these small groups. You can imagine each one is a household, and like one person is going out and probably working and then coming back inside, right? And then one other way to do it is to create a random geometric graph where the number of connections is roughly proportional to the distance between the nodes, right? And so we use these to run, what would happen, because there's no scope for experimentation here. We can't do A/B testing where we say, look, we're going to do first degree tracing for a set of people and multiple degree for another one. There's no time, and it's not probably ethical to not, use your best capacity for a set of people, right? So now we did these simulations, and if you look at this, when you run only first degree, that is the top half here. If you can see my mouse or pointer, I don't know. If you run that here, you will in this simulation you were able to notify 281 folks, right, who actually turned out to be infected, right? Now, if you look at the second list of results here, this is not a cumulative number. This is only second degree interactions. And you can see that in this setting, I believe we ran ring of cliques here, you actually identified more people at a higher baseline risk than only first degree, which means that a lot of people you are missing out, because in real world situations, you can imagine this, let's say at a grocery store, where there's one person so like let's say the cashier at a grocery store, that cashier is interacting with a lot of people and is getting risk, right? Now, let's say that cashier talks to the manager, and there are like 3 or 4 cashiers, and they talk to the manager who doesn't interact with people directly, but he's interacting a lot with his or her cashiers. Now, this manager may actually be at higher risk than any individual cashier because of the number of cashiers this person has been exposed to. But in a single degree contact tracing method, they will never be notified, and they will always remain at danger because they will only be notified once one of their cashiers actually gets an infection and is symptomatic and gets tested, right? So we thought that was suboptimal, and roughly on these simulations, this is like greater than 100%. But if you look at random graphs, then it came to around 30% effectiveness was reduced just because you're doing only first degree tracing, right? Now, we initially, before we even cover Wiretrace, we did initially, the algorithm we designed was based on basically a reverse risk propagation, which was recursive. So in very simple terms, what would happen is every device on itself, not on the server, would store a table of all interactions. And by table, I mean it would store the Bluetooth strength and the duration in an SQLite database on the device itself, right? And once a person would get infected, it would go back and update the prior of the other person. Let's say the prior was initially very low, maybe 0.001. It would go and update that prior to 1, because now we know that person was infected in the time window when that interaction happened. And once that prior was updated, it would recursively go back into the graph and update the priors for the other persons that the contactee connected to, right? And so on. It would propagate until it reached a threshold which was equivalent to the prior in the population. That is roughly how the initial iteration worked. Unfortunately, this was not numerically correct, and we had to go and correct it, and I'll explain why this was not correct. And this was something that we discussed with multiple experts, but this is something Ivan pointed out and convinced me and the team in a day, and we quickly corrected that. Now, look, in the Monte Carlo approach, what happens is everyone, let's say, it's a simple approach. Let's just first consider a single simulation, right? So let's say you're infected, you're assigned a bit of 1. That means you're infected. Now, to propagate that infection forward, whenever there's an interaction, you're going to roll a dice and say, okay, there's a probability of 10%, let's say P is 10, then with a probability of 0.1, the adjacent node in your network will get infected, and so on and so forth, right? And this is a simple Monte Carlo simulation. In this case, the interesting thing is that the actual value of probability is not going to change your risk ordering. It is by much, is what we found. It's going to change the number of people and the absolute probabilities, but not the relative risk ordering of people who are likely to be infected. And so we thought, instead of coming up with an a priori estimate of P, it would be interesting, because we had ground truth data, to come up with a posterior estimate based on the fact that we had data flowing in, and I'll come to that later as well. So that's a single simulation. In this case, the server coordinates the simulation by broadcasting a signal that a simulation has started. Pretty simple. And then each time the simulation advances by a step. In our case, the step was 1 day. It updates the bit of everyone around it. Now, obviously, a single simulation is not going to work, because that's too discrete, right? So the way we solved that was, instead of using a single bit, I mean, the way the Viratris approach solves that is you use a parallel, you use a vector, right? Which is, for the first infected person would be all ones, to show that they're infected in all parallel. Think of each bit here, or each row here, as a parallel world, right? And you're running the simulation. So what the state vector signifies here is that in the final one on the right, this means that out of 6 parallel worlds, this person was infected in 4 of them. And so that is an indication of the risk of the individual. It is important to not use point probabilities, which is what we did in our initial approach, because the transmission pathways are not really independent, right? And if you wanted to use point probabilities, then computationally the cost of the algorithm would become exponential, whereas the cost of this algorithm is not exponential, is much lower, I believe, n of order n, but in that case, it would be exponential and not feasible to actually do. Now, in multiple, this is why we run multiple simulations. The data collection aspect and the simulation coordination is the same. The only difference is that in messaging, in the messaging protocol, the content holds a binary vector instead of a single bit. Now, let me concretize it with an example. Okay. Now, in this case, let's say this red dot here represents an infected person who met with person A. Now, when we know that, and when we run the simulation, and we would choose to run the simulation 10 days prior. So let's say you're running a simulation based on data you observed today. So today somebody comes in and says that, and you find they are infected. So you measure the lags. So there's a lag between the person actually getting an infection to getting symptoms, then getting symptoms to getting tested, and to getting tested and getting the test results. And you have to make you have to go back in time so that you cover most of these lags with, let's say, greater than 99% probability, right? And in our case, that was like, we did 10 days initially. And so you go back in time 10 days and you look at the person's interaction starting from day -10. So if they're all ones, let's say there's some P here, then in the next person simulation, every bit will have a dice roll and they'll get another state vector. The next person after that is going to do the same thing. So it's going to go, and now wherever there is 1, then a dice roll will occur to determine whether B1 gets infected in the world. But where there is 0, there's no need to do a dice roll, because in this reality, A was never infected and can never infect B. And so this propagation actually takes care of multiple degree propagation in a very, I think, elegant and very accurate manner compared to using point probabilities. Now, when you do, there's a formal example we can do with point probabilities, but you can test it out yourself. Just assume point probabilities and assume that the transmission risk is 0.5. And in this graph, what will happen is C will actually have a higher probability of being infected than A, which is obviously absurd. A person in a single chain, who's further from the main infection source, cannot have a higher probability of being infected than a person who's earlier in that chain by definition, right? And so the point probability approach leads to these contradictions, because when you aggregate the probabilities at C without propagating all the way back to the graph, and you only consider the interactions CB1, CB2, CB3, and CB4, then we have to assume path independence of the infection, which is obviously not true because they all came from a single source. And I'm happy to share, a small write-up that we made on why this happens for anyone who's interested. Uh, Now, we already talked about the Monte Carlo steps. Now, there are two kinds of approaches here. One is a client-side approach, right? In a client-side approach, what you do is all the transmission vectors are calculated on every device, right? And the device sends a message, preferably through an end-to-end encrypted protocol like the Signal protocol, to another client, whoever they were in contact with, and then they process it. And so every device in this case, there's no need to even like there's no information that goes to the central server at all because it's end-to-end encrypted, and essentially people update each other's probabilities and they share information only with others at risk. And so this is, I mean, this is very secure, very, very nice. And, this seems to be the best solution. And the other one is the server side approach where, you get the interaction information from people, basis need, and then you run the simulation on the server. Now, the challenges that emerge are in a span when you're scaling up to 50 million users or 160 million users, in an environment where you're updating the algorithm constantly, right? I mean, by that time, we had already changed it once. And in a production environment, doing these changes in 4 or 5 days, as any person who's well versed in product or software engineering will tell you, is a big challenge because you don't want any points of failure. You don't want multiple versions of one app talking to each other and causing issues. Because you want at least some effectiveness rather than no effectiveness, or people or there being this mega breakdown and then people just uninstalling the app. So we're very, very paranoid about these things. And so we wanted a solution that could scale fast. And on a client-side approach, it becomes difficult because you can't just update 80 million devices at the same time. Every update that size has to be phased, even on the Android or app stores. And then what happens is that for a period of time, there are different people with different versions, and you have to handle that. And if you're making fundamental changes to the messaging protocol or to the risk propagation algorithm, then in that period of time, those people will not be protected by Aarogya Setu. So those were the pros and cons of both approaches. And this is an example of a difficult decision that we had to take. And in this case, we chose a server-side approach. The other element of the app that I wanted to discuss in terms of what it did was syndromic mapping. And this was spearheaded by a completely separate team. I did not work on this, headed by Professor Kamakoti of Madras, IIT Madras. And here the idea was that basis people self-reporting, right, their symptoms, and given the fact that location information is known, the density of that symptomatic signal was enough to predict with greater than 90% accuracy which area would become a hotspot about 10 or 11 days in advance. And this advanced information, which we believe was at least 4 to 5 days in advance of infections, this signal was super important because it helped Indian authorities redirect scarce resources to where it was needed the most. So testing infrastructure, we had our government procurement agency set up an entire format for temporary hospitals so that they could be procured quickly. And all of that would not have been possible at scale without this syndromic mapping. This is the user view that people got. So here you can see, your status, media, which had some, promotional videos by celebrities on why you should test and trace, and other health tips on the pandemic. We had a COVID update section, which had the numbers for every geography. ePass was an experimental feature, which would have enabled people to decide basis risk, whether to engage in, let's say, going out to dinner or not, right? And that wasn't implemented at this stage. But if you look at this, then in this case, the individual has a high risk of infection because they have had recent contact with an infected person. The app tells you some simple steps along with infographics like, isolate yourself from your family members, don't get tested now, get tested at this time, basis your history. After 7 days, get yourself tested. Here are all the labs where you can do it. Do self-assessment so that we can understand what your symptoms are like. This was a feature that we'll talk about later, which was very interesting, but it led to some issues which could have been avoided. But in this, it's a good feature. It tells you around you what are some metrics. How many people are infected around 500 meters, around a kilometer? How many people are reporting symptoms? It gives you a signal of how safe your area is. And we did it from the point of view of, open data. We believe that citizens should be allowed to kind of, or should get this information about themselves and their location so that they can take steps to protect those in their community. So fundamentally for us, it was an empowerment sort of decision for citizens to make this data available to them. In terms of security and privacy features, I'll cover quickly. We had a random unique identifier for each user. We stored all the interactions on the device until and unless you were infected. And this led to some challenges later with multiple degree propagation, which I'll talk about. In our privacy policy, we clearly said that your data, your interaction data only moves to the server in case you are infected, so that we can use that information to propagate the risk to others who may be infected. We were not allowed to take data from people who are at a high risk of being infected, but only from people who have been tested positive. That's why we could not do multiple degree tracing with a standard method, because we were not, empowered by a sort of privacy policy to do so, and we had to do a workaround for that. We added a location jitter. The reason we added that was when you look at this feature here of radius, if you don't add that, what happens is you could theoretically triangulate someone's location, but we added enough location jitter that it's not possible anymore to triangulate. And triangulation here means you can literally, if you moved around a location and then mapped how many users were changing, then think of it as like overlapping circles in a Venn diagram. You could find out in a smaller area than 500 meters who are infected. And this led to a needless controversy, but what folks who were creating that controversy did not realize was that there was a location jitter added. And if you add that jitter, then the overlapping area uncertainty becomes large enough that you cannot actually triangulate with any degree of certainty. We had a sunset clause on data. So after 45 and 60 days, all data on servers were, deleted. And there was no data that the government kept. These were some, I think we have less time, so I won't go over this, but the idea was to, even create an ecosystem around this, maybe with third parties who would not get information, but it would function as a check. Like if you go to a public place today, sometimes they take your temperature, which we all know, I mean, it's good that they do it, but it's not really a strong signal of whether you're infected or have a probability of infection or not. I think it's there. It mostly makes us feel better. But something like this, if folks consented to it, would be marginally better than that, where if you had a certain risk or you had been in contact, then businesses and establishments to take a call on whether you can dine in their establishment or not, or engage with their community or not. We didn't finally do that because of a lot of restrictions by Apple and Google in how to use this. We had to use our own solution, especially for iOS, to do reverse search. And what I mean by that is when there was a communication between Android and iOS, you could not get the DID directly. So in the reverse search algorithm, you would actually you would use to basically understand, given a device in a particular area, what were the Android devices that had come in contact with this device. So you would, instead of going from the iOS device and going and understanding what DIDs it had been in contact with, this algorithm would be able to tell you what, from the other device's point of view, what the contacts were. And it would do that by doing a geographic tile-based search, which it would keep expanding if that user was not found. And it was obviously computationally very expensive and kludgy, but we were forced to do it because there was no alternative because of the way these two ecosystems work. Now, apart from, I won't cover the first one, we already discussed it. The other two major architectural design choices were, should we only do Bluetooth or should we do GPS-based syndromic mapping? There's been a lot of press, for example, we had an excellent discussion with MIT, with Professor Chandrakasan and Professor Ron Rivest and others. But we did definitely feel that MIT Review had rated our apps, and we felt that it was actually very lazy journalism, because they had 3 or 4 parameters on the way they had rated their apps, and none of them was even effectiveness. So if you're judging every other component of the app, but its effectiveness in saving lives, then I think that particular categorization is pretty much useless and should be discarded, right? The other element was they kind of scored us that we were taking more data than was needed, because the public and sort of political narrative was that, GPS is not needed, right? And I believe that, the data shows otherwise. And people should be more data driven and more evidence based when they make these sort of sweeping generalizations. Because for us, GPS based syndromic mapping was certainly useful in a resource constrained environment, in a country, which is an emerging economy, where you don't have the capacity to buy, 10x of your population's vaccines. In an economy like that, it is super important to use your resources wisely, right? And GPS based syndromic mapping enabled us to do that with consent from people. It's not like we were forced. It was like, the people had a consent to deploy the app or not. And so we believe that, this was super important, and we took the stance to do GPS based syndromic mapping. We could have added differential privacy to it. We were doing some research around that area on how to do that. But in any case, all this information was only going to the server when a person was infected, right? So saying patently that this is extraneous information without any understanding of the country's climate or what it's empowering is not only lazy journalism. We believe it's like, it caused harm, because it caused a narrative that the app penetration could have been even higher. Even though this is the largest app by far in the world with 160 million users, we believe that number would have been even higher had this narrative, not been sort of this misinformation not being spread around by eminent pieces like that one. The third decision was whether to use the Apple Google APIs or phone Bluetooth data. Now, in Apple Google APIs, there were a couple of restrictions. One was in India, for example. Again, this is an example of how a lot of these innovations are sort of Western centric. The model of iOS that we had for most people in India would not have supported this anyway. And 60% of iOS phones would not support it. I believe 60 to 70% of prevalent Android phones, because in an emerging economy, these Android phones usually use earlier versions, are lower power devices, would not have been covered by this net. So we decided to use our own implementation, also because we could do multiple degree tracing, right? Which is clearly, basis our simulations 30% more effective. Apple, Google also for some reason took a call to say that if you use our, contact tracing framework, that same app cannot use GPS. I mean, we thought that was just, that's a call that citizens should take. That's not a call that someone sitting in an organization should take for an entire country, because it's about 30% more effectiveness in a disease that's causing deaths, millions of deaths. And I believe that it was not responsible to make these artificial restrictions without having an epidemiological understanding of how the disease progresses and what helps and what does not help. This is some of the results. Now, what I'll say is, please, like, the numbers are high, and these numbers stabilize to around 35% later, because we believe the numbers were high earlier because higher risk individuals probably self-selected to download the app. But this is as of 8th May, right? So if you look at the different risk categories, and here there are 4 categories: urgent, high risk, medium risk, and risk. Based on a sample size of at least 51 in the highest risk category, we were able to get positivity rates of 45%. So if we want about 80 means we actually, out of that sample, 51 were tested, and actually in terms of ground truth, 23 turned out positive within that 14-day window, and the algorithm had marked 191 people at risk, right? And so the expected positive cases out of 191 bases this information is 45%, because that's 23 divided by 51. And so it was 45% for the highest risk category. Even at the lowest risk category, this was very surprising for us that it was 20%, because there was no correlation between the risk score, which we made without a priori assumptions, and the actual ground truth data. I mean, there was correlation, but the actual ground truth data was much higher. And we believe this was because the digital graph is only a subset of the real world graph. And so what is happening is probably the individuals who have done 4 interactions are more likely to do many more interactions, because they're in many more unrecorded interactions. And I believe that's why we had a higher baseline risk. And this was much, much higher than the national testing efficiency, which meant that we should use this algorithm to allocate tests. Another signal here was the average amount of days that we had advanced information ahead of time. This entire tracing endeavor runs on advanced information. It's essentially an early warning tool. And we can interpret this graph, but basically it's like how many days of an edge did the algorithm give you basis the baseline, right? And it was 4.4 days on average. Another thing I wanted to highlight is the first Bluetooth calibration we did. Obviously, this became more sophisticated later. Was simply um, just uh, basis the average. So what we did was we took data of all Bluetooth interactions, and this is the RSSI graph. You can see there's a peak here, and we had like 2 days to launch this, and we had to understand what is the cutoff we should use to count as an interaction, right? And so the assumption that we made based on this data was that this peak here represents an interaction, because either folks are going to be far away from each other and it's an extraneous Bluetooth connection, or they're going to be close by and talking. And so we took this as a cutoff. And obviously this is not scientifically rigorous, but this is the data we had at that point. But even with that, even with these assumptions and not even accounting for calibration of these devices, we got this, right? So what this made clear for us is that a lot of the information here is hidden in the social graph rather than the specifics of the Bluetooth implementation. And obviously there are improvements that can be made to that, but the bigger problem was to get this out there and get this protecting people in the first place. I won't go over this. This is like, how we did multiple degree finally. So because we had that privacy policy, we could not directly run it. And what we did was we applied a just-in-time consent model. So what would happen is once you were once you were part of a multiple degree simulation, we couldn't automatically take your data. So you would get a notification that you have been adjudged at risk. Do you want to help protect others by sharing your interaction data? And once people gave consent for that, then we would run the simulation again and again and again. So we had to run, so this was computationally expensive because you had to get more people in the simulation by taking consent from them and running it repeatedly, and it did reduce its effectiveness. But there was nothing, we believe that privacy is important, and so we didn't want to just go ahead and do it anyway if people had not given their consent. And the challenge here was that we could have incorporated it in the privacy policy ahead of time, but this is all in retrospect. At that time we didn't even know we would do multiple degree. And the political economy here is, if you keep changing a privacy policy, there's going to be a negative narrative around it, even if it's done for very valid reasons, right? So a call was taken to not change the privacy policy and instead go ahead with just-in-time consent. Uh, I won't say too much, but the three top learnings from in retrospectively looking at this app. First one was around public communication and the phasing of features. So as I said, you know, the base product was contact tracing, and going back, the ideal thing to have been done is not incorporate features like, you know. Self-assessment and the feature that tells you a signal of your area, even though these are nice features to have, because it just increases the complication of the app and the public perception of the app. And people start making all kinds of theories, and there's miscommunication and so on and so forth. So if you were to go back in time, I would have advocated for making a super simple app that only does contact tracing and then add on features later once there's a critical mass of people. The second is an importance of a very strong privacy team, which can understand trade-offs between PII and effectiveness. In our case, we were not able to anticipate in adding the clause for multiple degree tracing, for instance, right? And so someone who can really calm-headedly and coolly take this call would be good in terms of understanding what to do in an app like this. And the third is the importance of a live and authenticated data flow that we had from the Ministry of Health through the ICMR testing laboratories and Ayushman Bharat. That was super important. Without that, there's no point of doing a contact tracing app, because if you don't have the input data, you're not going to be able to warn anyone, right? And a couple of things, just open to the audiences, things that we thought about. Could we have an international collaboration, maybe powered by WHO, some other organization, whoever, which can do contact tracing? Obviously, countries would not want to share citizen data, but there are ways to do this with secure enclaves where you only share. And we ran some experiments with homomorphic encryption, for instance, which I don't want to get into now, but essentially what it means is you can propagate the risk without and do those computations without having access to the actual data. So if there's enough research on that topic, then maybe there can be an international system in place which turns on contact tracing whenever there's an event, and that can be applied globally to constrain infections in a country or to quickly take policy actions like change flight schedules, etc. Should we have an early warning tracing and consent layer built into mobile OSs, or should we not? I think the pros are that it makes it native, makes it simpler. Cons are that obviously, advancements in epidemiology will not be incorporated as soon. Hard to change OSs, very hard to incorporate it into a build. And as we have seen, some of these companies are quite rigid on their views, despite overwhelming evidence to the contrary. Third one is, can we use something like this even for the flu? We don't talk about the flu often, but it also causes a lot of deaths. Any contagious disease can actually be covered by this model. Should we have that in place, and should people be using that? Happy to take questions. Sorry it went over.
So thank you very much, Aalekh. And I love the questions you bring up about, the decision between privacy and effectiveness. And so I'm just going to take the opportunity to remind people that March 11th is our next event, and it will be a debate on that very topic. But now I'd like to sort of go to the questions, which you guys can continue to upvote as I speak. But first in line there is Martin Walsh. Brandy, if you can let him speak. And then, you might want to modify your question a little bit. I think parts were answered, but hopefully, you can still tell us a bit more. And by the way, the chat is now also open just for comments as well. But questions, can you keep putting them in the Q&A and not in the chat?
Okay, sure. Should I just take questions one by one, or do you want to moderate?
Oh, so Brandy needs to promote them so that they can talk. So Martin is now, will now ask his question live.
Sure. Okay.
Hi, I'd like to thank you very much for the presentation. That was very interesting. And my first question is simply, if obviously when you started and when you first launched your app, that was before the GAIN protocol was available. If you had to start again today, would you use the GAIN protocol, or would you still work without it because you really didn't like the trade-offs that you had to do? As you've already said, you felt GPS was important. And also the second part of the question is, if not the GAIN protocol, you must have learned various things from your experiences. And if you had to do one thing differently, if you did it all again, what would that be?
Thank you for your question. Now, I will tell you that I've not been working on this for some time, and I'm not aware of the details of the GAN protocol. But to approach that question generally, yes, I mean, we were looking for good protocols that we could use, because nobody wants to reinvent work, and nobody wants to, build things that, are approximations. For example, our Bluetooth search engine, the fact that we have to run our simulations multiple times, so multiple degree, these are all things we had to do, not things that we wanted to do. So as long as the contact tracing protocol allows the app makers to make certain key decisions without imposing what I would call, within quotes, political decisions on them, such as whether you get to use GPS tracing or not, right? I mean, whether you get to use GPS data or not in a device that can actually collect that information and make it of use to you, we would use that. Yeah, I mean, our main considerations were, can it do arbitrary propagation? A, if it can, great. B, can it work between iOS and Android, specifically even those earlier versions? Can it do that? And three, can we also use GPS-based syndromic mapping concurrently with the tracing? If it satisfies these three constraints, we would have definitely used a protocol rather than rely on building something on our own in that quick of a time. With regard to your second point about what we would have done differently, I think the main thing is very simple. Would have gone, if I could go back in time, and if I had complete influence over the product decisions, which I did not. I mean, I was not the product lead. There was a separate sort of team for that. I would not introduce any features like like self-assessment, or even like telling people the signal in that area. I would just make it only basic, simple contact tracing and risk propagation. That's it. And folks would be given this information of how the app works in a simple infographic. When is your data collected, when it isn't? And I would very tightly control that narrative in the sense that, make sure that people don't have vectors to discuss things without information, because informed debate is great. I think it helps us move forward. But in a pandemic, when you're in crunch time, the debate is usually not informed. The debate is usually based on generalizations and people's fear of privacy invasion by companies in general, which they kind of layer onto this. And so you want to be able to control that narrative, because to my earlier point, you are trying to optimize the number of lives saved, and then you're trying to do that basis the PII collected, but these two things interact. You cannot optimize the number of lives saved if a large fraction of people, due to misinformation, do not download your app. And these are, I think, the things that really become important at scale.
So thank you. Let's move on. Can you, Rafi Yahalom would be the next question. Rafi, I think Brandy should be promoting you to speaker. There we go.
Yes, hi, can you hear me?
Yeah.
Oh, hi, thanks. A very interesting presentation. Thanks very much. Quick question on the numbers. I understand the numbers, the performance numbers you showed were a few months old. Are there more up-to-date numbers in terms of things like the positivity rate for the post-notification cases and things like how many on average contacts were notified by the app on the first or second degree?
This data, is currently, so the app, which was started by a consortium, is now currently being managed by an entity called NIC, India, which is the National sort of Informatics Center, and they should have this data if you send a request to them through whatever channel, and if they're if the policy is, we do know that since this graph that I showed you, it stabilized. Let me just actually go back to that screen. So the highest risk category stabilized at a number around between 35 to 40%, and the lowest risk category was between 10 to 12% around August, and it was pretty stable at those numbers, and was not changing. So I would be very surprised if that changed drastically. Although now that the infection has sort of turned a curve, I don't know what that would do to this, but I would be surprised if it's changed from that.
Thank you.
Okay, next, Andreas Gebhardt is the next question in line. Once he gets...
Okay, here we go. Hi guys. I'm kind of tying into the answer that you gave to Martin's initial question. So in looking at the conversation about trust and fear influenced or misinformation influenced public conversation, I'm curious to hear, what was the primary argument that helped people trust the app and the government with their data? Especially your early adoption numbers are pretty impressive. And so I'm really curious what kind of the public conversation and what arguments you guys were using that really drove that home.
Yeah, that's a really good question. And my colleague Arnab was in the midst of this firefight. Worked with him for 1.5 years while I was at NITI as well. I think better speak to this, but we used to have conversations on a live basis. And I think the primary thing in the communication strategy to build trust was openness. So a decision was taken very early on to kind of open source at least the Android version of the app and its components, so that people could themselves examine, what data flows are happening. And the idea was that sophisticated users could then analyze that and then pass on that information gradually to less sophisticated users and sort of then build trust in the ecosystem. So I think that was a very important tenet. The second thing was I think in a situation like this, it's also you want to make the choices very clear to people. Yes, I mean, you are when you are infected, you are giving up personal data. There's no doubt about it, in the sense that you are telling which DIDs are infected, but nobody can actually go on the development team can actually use that. They don't even know your name. So we had a lot of information campaigns based on very simple messaging around how DIDs were abstracted away from your actual identity and how those were used for risk propagation. And then finally people were notified. But yes, you are giving, and I think the idea is to elevate this debate into an informed debate. So there is a trade-off between privacy and effectiveness. It's not that you can build an app with zero privacy, like zero data being shared and full effectiveness. That doesn't happen. So some of the debate was so uninformed that it was like, why doesn't the government just build an app that does not use personal data? Well, you can't. You can't build an app which is warning people, which does not use any data and does not link to your phone number. So first was confronting them with this reality. The third, and I think most effective was we started giving these numbers out in public about how effective the app was. And then we had a lot of stories as well. So there were individuals who came up and spoke about how they were able to protect their elderly parents or grandparents from COVID because they had gone to a party and then they came to know 4 days ahead. So I think those things connect more with people, individual stories, and raw data. So I think a combination of these strategies was what we eventually ended up using.
Sure, thank you.
Okay, there are still lots more questions. The next one's from somebody anonymous, which was just, how did you track who was alerted and then later confirmed positive?
Who was what, sorry?
So when somebody was alerted and then, when you're getting your positive predictive values, how did you track? How did you link the fact that they were notified and then the fact that they were positive later?
Right. So the way we linked is, the device identifier, right, which was declared at risk at a particular point in time. Let's say today there's someone who comes up as being at risk through your simulation. Then when that same person gets tested, maybe 4 or 5 days later, that data also flows back through to us through the ICMR link through a backend APIs. So then it goes back to the server, because when they fill in their ICMR form and they say, look, I'm getting tested, and their mobile number, that is linked to their DID. So then we get another list that these device identifiers were confirmed positive, let's say 6 days. And if it's within the infectious window, then we can track that and say that we want someone who later was found infected within an infectious window. Obviously, you want to have that time constraint built in, because otherwise, you can just randomly select 3 people, and then when infection rates are very high, you can claim to have predicted that. But that obviously has no predictive value. Hopefully that answers your question.
I think so. Well, it's anonymous, so we can't check that it does. But so next, I would say a number of people, including Michelle, who's coming up, have been asking about whether your slides are available. And I just wanted to say that all the videos, the complete video stream, will be posted to the Science of Pandemic Tech website. And then, Aalekh, it's up to you whether you also want to post just the slides without the whole recording. But anyway, yeah. Michelle, you want to ask the rest of your question?
Hi, first, thank you for the presentation. I was wondering what the geographic distribution of your adoption looked like, and if you did any targeted communications or marketing based on that.
Yeah. Again, I was not on the communications and publicity side, and I'm really, really thankful for that, because it's a huge challenge for a country like India. But what the main strategy was to have the downloads where the infection rates were the highest, right? And so there was constant tracking by the highest offices, government offices in the country, of where there were infection rates, which were going high, and where app downloads were also high. And these tended to be in cities. So there are a number of articles around that how the propagation rate was significantly higher in cities. And obviously, in a country like in India, the smartphone penetration is still not like, is very high, but it's still not high compared to the Western world. And so there were pockets that you cannot get to. And for them, we were using IVRS-based solutions, which was also integrated here. So, through normal, let's say, feature phones, they were getting calls, and at least some symptom information was coming through from there, that, in this area, X number of symptoms were reported. But obviously, you couldn't run an app. There was an effort which had Aarogya Setu run even on a geophone. A geophone is like a very low powered, it's a different, it's a 4G phone, which runs a different OS, and Reliance Jio then ported our app over there as well. So that covered a significant amount of people who could not afford an Android or an iOS smartphone. And yeah, so the geographic targeting was mainly where the infection rates were higher. Beyond that, it was an all-out push to get as many people with smartphones to download. The main metric for us is what proportion of the smartphone population are we able to target. Now, there are other programs in the country that are helping people without smartphones, but for digital contact tracing, we want to be on as many Bluetooth devices as possible. That was what our objective was.
So I'm afraid we're out of time. I just want to make sure you answer the last part of it. Are you also going to share the slides, which we can post on the website, or will it be just the recording?
Can you post the recording from now? I think for this, I just check with the team, but hopefully I should be able to share it. I'll get back to you.
Okay. All right. Well, thank you everyone else for attending. Sorry for those we didn't get to your questions before we ran out of time. Please join us again March 11th for the the debate that we're going to have on privacy versus effectiveness and who should be making these decisions and how and all of that kind of thing. And please come back.
Thank you, Joanna. Thank you, Luca. This was a good opportunity to share from my side. Thank you for the questions.
Yeah, and we're all envious of the adoption that you've achieved in India and the extraordinary predictive power of the app. I'll just say that it's just extremely impressive.
Thank you.